In this video, we'll explore the world's fastest improving new solar technology and provide an exclusive peek inside the lab of a team working on this breakthrough material. Right now, while you're watching this video, a giant fusion reactor 93 million miles away is irradiating the Earth with about as much energy as all of human civilization uses in a year. So why aren't we harnessing this abundant, renewable energy source to meet all of humanity's energy needs? It's not an issue of physical impossibility. If you wanted to power the entire US with solar panels, it would take a fairly small corner of Nevada or Texas or Utah. You only need about 100 miles by 100 miles of solar panels to power the entire United States. Currently, only 2% of global electricity comes from solar power, and 90% of that comes from crystalline silicon-based solar panels, the dominant material technology. While abundant, silicon has downsides related to efficiency, manufacturing complexity, and pollution that prevent it from being an absolute no-brainer. Now, what if I told you about a material that was lighter, more efficient, and simpler to produce at a lower cost? An inexpensive solution that can make a photovoltaic cell so thin that just half a cup of liquid would be enough to power a house. A solar panel so lightweight that it can be balanced atop a soap bubble. Well, that, folks, is known as the holy grail of solar. They're called perovskites, and they might just revolutionize how humans generate energy from sunlight. We headed to Silicon Valley to meet Joel Jean, the CEO of Swift Solar, one of the leading teams working to bring perovskite solar technology to light.
It's a new kind of thin film technology, so you've probably heard of that for a long time. Different kinds of thin films have come and gone over the years. What we do here is a new kind of material. It's called perovskites, new semiconductor material that absorbs light really effectively, also transports charge. So it just turns out to be very efficient material for solar cells.
Solar cell technologies can be classified into two categories: wafer-based or thin film cells. Wafer-based cells are fabricated on semiconducting wafers and are usually protected by a material like glass. These are the crystalline silicon cells you'll typically find on bulky roof-mounted solar panels. Thin film cells are made by depositing thin layers of semiconducting films onto a glass, plastic, or metal substrate and use 10 to 1,000 times less material than crystalline silicon cells. These thin film cells are light and flexible but have lower average efficiencies. You can make thin film cells from amorphous silicon or more complex materials like cadmium telluride, but scientists have been on the hunt for better thin film solar technologies that can see more widespread use. These materials are known as emerging thin films. Currently, perovskites are the leading contender. What could you do with a solar panel with 100 times the power-to-weight performance of conventional silicon panels? A solar material so abundant, it could be painted on skyscrapers. Flexible, lightweight, highly efficient cells could open up a wide range of applications where traditional silicon cells are too heavy and rigid. But before we cover your Tesla Model S Plaid in perovskite solar, what exactly is this revolutionary crystal? The perovskite crystal structure was first discovered as the naturally occurring mineral calcium titanium oxide, but the perovskites used in solar cells don't need to be mined from the Earth. A perovskite is any material with a crystal structure following the formula ABX3, where A and B are two positively charged ions, often of different sizes, and X is a negatively charged ion. Scientists realized that they could create a diverse range of man-made perovskite crystals following this same arrangement that have very useful properties.
So we use basic metal halide salts, so things like lead iodide or some organic salts as well, and we combine them to make these inorganic, organic hybrid perovskites. So if you can form them in solution, you can form them in vacuum, out of vapor phase, and they condense into forming these perovskite crystals. And the thin films, they're like multi-crystalline, which means that there's a bunch of little crystal domains. They turn out just to be really good semiconductors.
So just how efficient are perovskite solar cells? The most efficient modern silicon solar panels you'd find on a home only work best at around 20% efficiency. But the theoretical conversion efficiency of single-junction solar technologies is about 33%, called the Shockley-Quasar limit.
That's the fundamental limit for a single solar cell, single material-based solar cell. Perovskites are the exact same thing. Silicon perovskites, cadmium telluride, CIGS, all of these technologies have the same limit.
But perovskite solar cells can be made in a form factor that's capable of much higher efficiency limits, pushing the boundaries of possibility for solar power. To understand why perovskites hold an advantage over traditional silicon solar cells, let's first do a basic refresh of how photovoltaic cells convert sunlight to electricity. The top and bottom parts of a solar cell contain semiconductor materials with different electrical properties. In a traditional silicon cell, for example, silicon is used for both layers, but each layer is modified or doped with tiny amounts of different elements to create different electrical charges. The portion that contains a higher concentration of free negatively charged electrons is called the N-type region, and the side that contains more positively charged holes, or missing electrons, is known as the P-type region. The boundary between these two layers is known as the P-N junction. When an N-type and P-type material are put in contact, free electrons from the N-type material and free holes from the P-type material move across the boundary and cancel each other out. The electrons fill in the holes. This uncovers the fixed positive and negative charges of the dopant ions, which creates a built-in electric field that stops more electrons and holes from moving across the boundary. This electric field corresponds to a built-in voltage and acts like a one-way valve for charge carriers. The fundamental unit of light is the photon, which represents the smallest packet of electromagnetic radiation of a given wavelength. When a photon from sunlight hits a solar cell and gets absorbed, it creates an extra free electron and hole, which are separated by the electric field and pulled to opposite sides of the cell. This creates a photocurrent. If electrodes are attached to both sides of the cell, forming an electrical circuit, an electric current will flow as long as the sun is shining. The magic of perovskite crystals lies in their customizability. Single-junction solar cells can only absorb a portion of the solar spectrum depending on what semiconductor material they use. The lowest energy of light that can be absorbed in a semiconductor is called its band gap. A semiconductor will not absorb photons of energy less than the band gap, and the useful energy that can be extracted from a photon is no more than the band gap energy. This means much of the energy in sunlight goes to waste when it hits a single-junction solar cell. But because the band gap of perovskites can be easily changed, you can stack perovskite layers on top of each other that are chemically tuned to absorb different parts of the solar spectrum. This results in a solar cell with multiple p-n junctions that can produce electricity from a broader range of light wavelengths or extract more energy from each photon, improving the cell's efficiency.
So when you stack two solar cells on top of each other, that's called a tandem or a multi-junction solar cell. And when you do that, that actually pushes that efficiency limit up from 30% to over 40, about 45 or 46%.
Theoretically, an infinite number of junctions would have a limiting efficiency of 86.8% under highly concentrated sunlight.
And it goes higher with more layers, but it also becomes more expensive and you get diminishing returns. So generally we talk about doing 2 layers or making a tandem. And that's kind of the real selling point of perovskites.
So perovskite tandems convert more of the sun's energy into electricity rather than wasting it as excess heat. What are the exact efficiency percentages we're talking about here?
We shouldn't expect solar cells above 40% efficiency, this kind of solar cell, for a long, long time. I think in theory it could get there, but realistically I think in the 30s is doable, which is still a substantial jump from what you see out there on the market today.
It's not just performance that's improved. The nature of perovskites allow for manufacturing advantages too.
So you only need less than 1% of the material that you need for a silicon cell to absorb all the sunlight. So in theory, you can save money. You can basically make this stuff a lot cheaper. The cool thing about the perovskites is that they turn out, even though it's made of this kind of not perfect material, you can actually make a very, very efficient solar cell. It's formed at low temperatures. Silicon usually you have to crystallize at something like 1400 degrees Celsius. With perovskites, you can form it at less than 100 degrees Celsius. So that means that you can actually use smaller equipment. You can kind of use more standard chemical processes, and you can form these solar cells on things like plastics. So things that would melt under high temperatures, you can actually use to make solar cells on. So you can make something really lightweight and flexible as well.
Perovskite thin films can be made by synthesizing a solar ink of sorts and gently heating it until the perovskites crystallize, just like salt crystals emerging from evaporating seawater. Now let's go deeper into the lab to take a rare and exclusive sneak peek behind the scenes to see how perovskite solar cells are made.
Yeah, so this guy is called a thermal evaporator. So it's one of many kinds of deposition tools that we use to put down thin films. So when you look at a perovskite solar cell, it's like any other thin film device, like an organic LED or a cadmium telluride solar cell. It's got a lot of thin film semiconductor layers. And one of the ways you deposit some of those layers is using techniques like thermal evaporation, where you heat up a source material, or maybe it's silver, or maybe it's a precursor for one of your semiconductors. And you melt it, you evaporate it, and then you have a cold surface that you condense on. And that cold surface is actually just at room temperature. It's a plastic sheet or a glass sheet, or even a silicon wafer that you're trying to deposit a film on. The substrate sits at the very top of the chamber. It's under high vacuum, and you, again, evaporate this material, and it condenses and forms this uniform thin film. And you do that many, many times with different kinds of techniques, and that gets you your solar cell.
You can also make perovskite cells with spin coating, screen printing, electrode deposition, or even printing the material on a sheet just like an inkjet printer. Here's the end result, a small rectangular perovskite solar cell.
So this is the side that's facing the sun,
Correct.
and this is the back of the cell.
Yeah. The side facing the sun is actually, you're looking through the glass, and on the other side of that glass there's a perovskite layer kind of sandwiched between the contacts. So the contacts are what pull the charge out of the perovskite. So there's a transparent conductor on that, on the side closest to us. Then there's the perovskite, and then on the other side, if you look at it from the back side, there's these silver electrodes, and it can be any different kinds of metals, but that side doesn't have to be transparent because you actually want the light to reflect back into the semiconductor, not go through.
These solar cells are just lab samples designed to test different perovskite formulas.
And you can see that these different pads, each of these squares is a solar cell. So we have 6 different solar cells on one substrate for R&D purposes, for testing.
Swift Solar is trying to create a perovskite solar cell with a perfect mix of longevity and efficiency ready for commercialization. So how do you test the cells if it's a cloudy day? The sun can be quite unreliable, even in California.
We actually use this machine right here. So this is it's called a solar simulator. So it's actually just a fake sun. It's an LED array that basically has all the colors basically. It has a lot of different colors of LEDs, something like 20 different LED colors in an array with optics to make it really uniform. So the idea is here, we don't want to have to take our solar cells outdoors and test. If it's raining, we can't test our cells.
What are these here? Are these the circuit boards at the solar panel that measure the voltage when the solar panel sits on top of them?
Yeah, it measures the voltage and current. So this is, you can kind of see this, it's the same shape and it's got a bunch of pads on there. And each of those are basically leads to pull out current or measure, to measure voltage, or apply voltage. So you can see we can do 20 of these at once. And it basically automatically moves around to test the cells, each of them individually.
Perovskites have improved greatly since scientists first began testing them, and are now beginning to surpass mono and polycrystalline silicon cells in conversion efficiency. As perovskites start coming into commercial usage, where are we most likely to see them first?
All the traditional solar applications on your rooftop, out in the field somewhere in the desert, on commercial rooftops, on residential rooftops, those are all fair game down the line. Perovskites aren't ready for that kind of prime time yet. Stability is still a challenge, getting them to last for 25 years. No one can say that yet confidently. We don't have the field data to prove that. So there's a lot of engineering work and science to be done to get to that point. But there's a lot of applications where you don't need 25-year life, right? Like a car maybe only needs 10 or 15 years. There's things like high altitude drones, right? Which are going to be fully powered by solar. They're flying in the stratosphere at 65,000 feet, beaming down internet. So that kind of thing needs very, very lightweight solar. It needs very efficient solar. It doesn't need a 25-year life. You maybe only need a couple years, 5 years. So that kind of thing you can imagine being powered by perovskites very soon. Same with solar wristwatches or small IoT, Internet of Things devices. There's a lot of these kind of mobile applications where you could imagine perovskites kind of coming into the market and then eventually improving towards the rooftop, towards the utility scale applications.
So what exactly are the challenges that are preventing perovskites from dominating the solar energy landscape and changing everything?
We've spent a lot of time in this lab actually working on the challenges of developing this technology to a point where it's ready for production and for scale up. There's things like stability, which is probably the core problem for perovskites, is how do you make these cells last effectively for years in the field under high temperatures? Car roof might get up to 80 degrees Celsius, right, or more on a hot day. So you need to be able to survive those temperatures for years at a time. And I think we do a lot of tests and iteration on the materials, on the device stack, the stack of materials we use, on the design of the device itself, on the packaging, to make sure that we can survive those kind of temperatures, high humidities, the different kind of environments you face outdoors.
The relative fragility of the perovskite material requires protection to shield this semiconductor layer from environmental stresses and degradation. The international standards for terrestrial solar panels require harsh testing that simulates 25 years of being outside. In these tests, panels are heated up and even battered with simulated hailstones. The problem with perovskites is that they're still relatively new. We can subject them to these harsh simulated tests that give us a pretty good idea of their longevity, but we just don't have the real-world data yet, like we do for silicon panels, which have been in use for decades now. While perovskites are still in the research and development phase of the technology lifecycle, there are many teams all over the world working on improving their efficiency and stability to bring them into commercial adoption. The raw materials for perovskites are abundant around the world, and the solar cells can be made using relatively simple manufacturing processes. This means that perovskites can rapidly scale when they're ready for mass market commercialization. It's estimated that perovskite panels could cost up to 15 times less per watt than modern commercial silicon solar panels. In addition, engineered perovskite materials absorb all parts of the solar spectrum efficiently to produce the highest possible power output, and ultra-thin films open the door to new product formats with unprecedented power-to-weight ratios and high flexibility. A future with cheap, abundant solar power could open the door for a variety of use cases where current photovoltaic technology does not yet make sense. How about these electric yachts I filmed for previous Electric Future videos? Their range could be radically improved with higher efficiency, lightweight, integrated perovskite solar panels. We could see integrated solar panels on trucks, buses, and cars, and any other applications where sunlight is not yet considered energy dense enough to provide meaningful power. Imagine buildings covered in transparent photovoltaic glass windows that generate electricity. It's difficult to predict the future of solar. While perovskites are promising, serious researchers avoid playing favorites. Instead, they view all technologies objectively, based on increased efficiency, reduced materials usage, reduced manufacturing complexity, and cost. Solar photovoltaics are the fastest growing energy technology in the world today, and a leading candidate for terawatt-scale carbon-free electricity generation in our lifetime. If you'd like to better understand some of the concepts we presented in this video, it's important to first learn the fundamentals of solar energy. Brilliant does a great job of taking complicated science and breaking it down into bite-sized pieces with fun and challenging interactive explorations. Master concepts, grasp the fundamental principles, and develop your intuition so you can truly understand these breakthrough technologies. I've taken Brilliant courses on electricity and magnetism and solar energy, and was impressed with how well they structured their lessons with clever analogies, examples, and quizzes to test your knowledge. Brilliant offers a wide range of other content and topics from mathematical fundamentals to quantitative finance, from scientific thinking to special relativity, from programming with Python to machine learning. Go to brilliant.org/electricfuture and sign up for free. And also, the first 200 people to go to that link will get 20% off the annual premium subscription. We showcase cutting-edge sustainable technology. If you enjoyed this video, please give it a like and subscribe to our channel. You may be interested in watching one of these videos next. Thanks for watching, and let the volts be with you.